Okay, so we just factored our denominator, and I know that the only irreducible factors of a polynomial in the real numbers, oh, feeling very qualified today. The only possible factors are linear factors, right, ax plus b, or quadratic factors, or degree 2 factors if you prefer, ax squared plus bx plus c. Why did we do that? The reason is we're going to take our rational function and we're going to split it down into pieces that have those same factors that we just found as their denominators. Every time I have a linear function, or a linear factor, excuse me, I'm going to build up a fraction, a rational function, that is just some constant, we'll call it capital A, divided by my linear term. We'll get back to this exponent in a minute, just hold tight. The other possibility is when I have quadratic terms that don't reduce, right? So this is just like my x squared plus 4 on my last video. If you have something like that, we're going to look to build a rational function where the numerator has a linear polynomial, so some ax plus b. And these are capitals because they could be different coefficients than what I have on the denominator. So that's kind of what I want to be doing with my factorization. Again, there's this exponent here that I'll get back to. And fortunately enough, while we're doing that, there's only 4 things that could happen. We're just going to list them out. These are the rules for what to do. Number 1, the denominator, remember back, denominators, rational functions, they have those. We factored them. Case 1 says the denominator is a product of distinct linear factors. So they are all different from each other. There's no repeats. What you're going to do in this situation is this. So, right, here's the factorization. Yes, that's, yep. Here's what we do. We are going to solve for some new coefficients. So this slide is calling them capital A1, capital A2, capital A3. And those are for exactly 1 for each of those linear factors. So my rational function that's giving me grief is going to split down into these nice rational functions. Some constant divided by linear term, some constant divided by linear term. And this is all looking very abstract, but I at least know how to integrate those. I can do all of those with a U substitution. Well, maybe each one will have its own U substitution, but I can do them. I can integrate them. I can. Here's how we calculate those capital A's. So here's a rational function. Let's integrate it. The degree of the numerator is less than the degree of the denominator. That's very nice of them. So this is our example here. We don't need to do the long division step because it's already been done for us. Moving on. Next step, factorization. Can you see the factors already? I can see one. So because every one of these terms has an x in it, I know I can factor out an x. And that does count as a linear term, so that's one of my factors. And I get 2x squared plus 3x minus 2. The slide is nice enough to tell me the factorization of that polynomial. So I have total of 3, count them, 3 distinct linear factors. Okay, so remember, we're going to take my rational function, break it into 3 pieces. Each one of those separate pieces will have one of these factors as its denominator. So that's going to look like this. Now, because I know that I only have 3 of them, I guess you could call these A1, A2, A3, but it's more common to see like a capital A, capital B, capital C. They're just placeholders. The only important thing is that we're able to tell which one goes where. Beyond that, you can call these alpha, beta, gamma. You can use katakana, whatever you want. We're just doing algebra. Right. So how do we actually solve for these numbers? So we're going to solve for these by multiplying both sides of the equation by the denominator. Which denominator? This denominator, this one right here, the one that we already know. I'm multiplying both sides of this equation by x times 2x minus 1 times x plus 2. That's going to clear denominators on both sides, and now I just get regular polynomials. So I get this. Now, again, the slides have suppressed the steps, and I feel like I'm sort of on a rant here. So you might need to pause the video and double check that this is all making good algebraic sense. But am I closer to finding the A, B, and the C? I think so. I really do. Let's keep working on this. So we're going to expand the right side of that equation. And we're going to put all of the x squareds together. Here they are. There's a 2 times ax squared, there's a bx squared, and there's a 2 times cx squared. We're going to bundle them all together. I'm going to do the same thing for the x's. And there is another typo. There should be an x here. There's a 3 times ax, there's a 2 times bx, and there's a negative cx. It's supposed to be an x. Anyway, and we're going to group all the constants together. The only constant is my negative 2a. So frustration aside, we have polynomial on the left equals polynomial on the right. We grouped all of our coefficients together when they have the same power of x. What does that mean? Well, that means that this stuff in parentheses here times the x squared has to be equal to 1x squared. This stuff in parentheses times the x, that they forgot to write, has to be equal to 2 times x. This constant, minus 2a, has to be equal to this constant, plus 1. So that gives us 3, count them, 3 equations to let us solve for 3 variables. So there's our equations. We can solve this system of equations using algebra. And here's the solution. A is the number 1/2, B is the number 1/5, and C is the number negative 1/10. So that allows me to rewrite the rational function as these 3 rational functions, and each of them has its own antiderivative involving the natural logarithm function. And since I already used my plus c as, one of the coefficients I was solving for, I got to use something else for the constant of integration, and I guess this slide goes with k. Okay,